In this collection of videos, I'm going to be talking about derivatives. I will be talking about them in full generality, but I will be very much focused on thinking about derivatives in how we will be using them in a data science field. So this isn't a particularly mathematically heavy approach to derivatives. So as a motivation, I want us to consider this specific function, which is just a polynomial, but not maybe the nicest polynomial we've ever seen, on a particular interval, and the interval I have chosen for this function is from 0 to 10,000. And the question I'd like us to consider is, can we find the maximum and minimum values of this function on the interval from 0 to 10,000? So before we go any further in the slides, I want you to pause and think critically about a couple of questions. First of all, where do you think these maximum and minimum values are? And how confident are you that your answer is correct and as precise as can be? Second of all, once you have your idea for where the maximum and minimum values are for this function, how would you use a computer to find the maximum and minimum values? And how would you have the computer gain accuracy on determining those maximums and minimums? So pause, take a moment, think about those things, and then in the next couple of slides, I'm going to go over some possible answers. Now, I think the first possible answer to this question that comes to mind is, you've already created a graph of the function, why don't you just take a look at it? And when you do take a look at our function, I see perhaps 4 different places that I would investigate further for maxes and mins of the function. I see something right here, over towards 0. That's a pretty low value of the function. Right up here, which appears to be somewhere around little after 2,000, probably before 3,000, we see a potential maximum of the function. Our function then dips back down, and around here, maybe 7,000, 7,500, we see what could be a minimum value. It's very difficult to tell from the graph whether this value or this value is lower. And last but not least, we have this value at the end, right up here at 10,000, that's rather high. Again, questionable whether or not this value of the function is higher than this value of the function. Now, one immediate drawback of this particular solution is that although looking at a graph of the function allows us to zero in on points of interest more quickly, we're not being incredibly accurate or specific as to where these max and min values occur and what they might be. We're only able to get broad ranges of what we think those input values might be, and around 20,000 for a maximum, around maybe a couple hundred for this minimum value, we can only get in the ballpark by glancing at them. So looking at something is very quick for narrowing our attention, but it's not very accurate. And another immediate drawback of this situation is that it's very difficult to tell a computer to look at something. How does a computer look at a picture? That's a much more difficult question. So if you're approaching this problem from a computer science angle, you might say that the computer has no ability to really look at a graph, but one large strength of computers is their ability to compute many things very quickly. So one thing we could do is go into Python and define a function called poly that is the polynomial in question. We could make a list then of all outputs of that polynomial function for the x values on our interval from 0 to 10,000. And we could ask the computer to find the maximum and minimum values. This thing we have right here called maximum and this thing we have right here called minimum would tell us the output values of the function that are the max and min. And we could use the index method of a list to identify those x value inputs where we achieved that maximum and minimum value. And a computer can run something like 10,000 computations in a heartbeat, and so this line of code right here would be just as efficient as looking at that graph and coming up with an answer. And we should get an answer that's accurate down to within about 1 unit. So not only would this amount of code be just as fast as a human being glancing at a picture of a graph, it would be a lot more accurate to within 1 unit. Likewise, if we craved more accuracy from our computer, we could very easily modify this approach to not only be looking at output values of the function on integer input, we could do some clever tricks to make a much larger list that checks the output value of our function on a larger collection of inputs. So perhaps we wanted to get something like 2 decimal places of accuracy. We could run through in steps of size 0.01 and check not just integer values 0, 1, 2, 3 and outputs of the function in that sense, but we could look at outputs of the function at 0.0, 0.01, 0.02, and so on, run essentially the same code, and we could gain 2 digits of accuracy this way. However, if you're looking at a very large range of possible input values, and then you want to get a couple digits worth of accuracy, you're going to create a very large list here very quickly. And even here, where I have something like 1 million values in this list for my computer to check, Python takes a second to do this amount of code, and so you'd have to be really cautious if you were dealing with a larger interval or if you craved many digits of accuracy. This level of brute force computation for something that needs to be very accurate or is a very large input size is going to be a little bit too much for our computer to handle. So we'll have to be a little bit more clever than this, even though this is a really good first attempt.